In this lecture, we discuss about Fourier series expansion of a function. Before that, let us take some basic definition of periodic function. A function f(x) is said to be periodic if there exists a positive number t such that f of x plus t is equal to f of x for all x. Here, capital T is called period of the function f of x. It means that any function fx which repeat itself after t time, so that is called periodic function, and the time at which the function repeats to itself is called period of the given function. So here f of x is periodic function and the period of the given function is t. Let us take one example. The trigonometric functions sin x, cosine x, sec x, and cosec x are periodic functions with fundamental period of 2 pi. Why? Because after 2 pi, these four functions repeats to itself. Example number 2, the trigonometric functions tan x and cot x are periodic functions with fundamental period pi. Example 3, the constant function f of x, which is equal to c, is periodic function. Every positive number is period of constant function. Example number 4, the functions sin nx and cos nx are periodic functions with fundamental period of 2 pi upon n. What is Fourier series expansion of a function? And Dirichlet conditions. Any function f of x in the interval c to c plus 2l, or we can write down open or closed interval. We are considering here the closed interval c to c plus 2l can be expanded in terms of Fourier series if the following conditions are satisfied. The first condition is f of x is periodic function in the given interval c to c plus 2l. Second condition, f of x and its integral are finite and single valued in the given interval. Third condition, fx has at most finite number of finite discontinuities in the given interval. And the fourth condition is fx has at most finite number of maxima and minima in the given interval. If any function f of x will satisfy all these four properties or conditions in the given interval c to c plus 2l, then we say that that function can be expanded in terms of Fourier series. For example, fx is equal to sine inverse of x cannot have a Fourier series expansion in any interval since it is not a single valued function. Because if you put x is equal to 1, then sine inverse of 1 is equal to pi by 2. Sine inverse of 1 is equal to 2 pi plus pi by 2, 4 pi plus pi by 2, 6 pi plus pi by 2. So for one value of x, we are getting the multiple value of f of x. Therefore, it is not a single valued function. Example number 2, f of x is equal to 10x cannot have a Fourier series expansion in 0 to pi since it becomes infinite at pi by 2. Example number 3, fx is equal to 1 upon x minus 2 cannot have a Fourier series expansion since it has infinite discontinuity at x is equal to 2. These are some examples of a function which cannot be expanded in terms of Fourier series. Let us define what is Fourier series. Fourier series of a periodic function f of x in the interval c to c plus 2l, means c is less than or equal to x, x is less than or equal to 2l, that can be also written as C2C plus 2L is given by f of x is equal to a0 by 2 plus summation of an cos n pi x upon L plus bn sin n pi x upon L from n equal to 1 to infinity, where a0 is 1 upon L integration of c2 integration under the limit c2 c plus 2L of f of x with respect to x. Similarly, an is equal to 1 upon L integration under the limit c to c plus 2L f of x cos n pi x upon L with respect to x. And bn is equal to 1 upon L integration under the limit c to c plus 2L of f of x into sin n pi x upon L dx. This is Fourier series of any periodic function in the interval c to c plus 2L. Now, in the next slide, we see if we change the interval, then how we are able to write down the Fourier series. Now we want to write down the Fourier series of a periodic function f of x in the interval 0 to 2L, which is given by f of x equal to a0 by 2 plus summation from n equal to 1 to infinity of an cos n pi x upon L plus bn sin n pi x upon L. So if we see the previous definition of Fourier series and this definition of Fourier series, here there is no change. Only change will happen in the when we are calculating the value of a0, an, and bn. What is a0? A0 is 1 upon L integration under the limit 0 to 2L of f of x with respect to x. Similarly, an is 1 upon L under the limit 0 to 2L f of x cos n pi x upon L, and bn is equal to 1 upon L integration under the limit 0 to 2L fx sin n pi x upon L with respect to x. So clearly, if you see the previous definition of Fourier series and this definition of Fourier series, the series is, there is no change in the series, but only while calculating the value of a0, an, and bn, the limits are only changed. Let us take another form of the Fourier series. If we change the limit, what will happen? Now, we want to write down the Fourier series of a periodic function fx in the interval minus L to plus L. Again, we are getting the same Fourier series, only the values of a0, an, and bn are changed, and it is only changed what is the interval of the or limits of the integration. Otherwise, rest of the things are similar. And now this L is any arbitrary number. If we can put any value of L, correspondingly, we are able to get the Fourier series. Now let us try to find out the Fourier series in the interval minus pi to plus pi, which is given by f of x equal to a0 by 2 plus summation from n equal to 1 to infinity a n cos n pi nx plus b n sin nx, where a0 equal to 1 upon pi integration under the limit minus pi to plus pi f of x dx. An is equal to 1 upon pi integration under the limit minus pi to plus pi f of x cos nx, and bn is equal to 1 upon pi integration under the limit minus pi to plus pi f of x sin nx with respect to x. Now here, if we write down the previous definition, f of x is equal to a0 by 2 plus sum of, let me enlarge it, f of x is equal to a0 by 2 plus sum of n equal to 1 to infinity a n cos n pi x upon L plus b n sin n pi x upon L. Now here, if you put L equal to pi, if you put L equal to pi, what will happen? This will become pi and pi will cancel. This pi will cancel. So we are getting a in cos nx plus b in sin nx. Therefore, if you put L equal to pi, then the Fourier series is changed like this. And their values for a0, an, and bn are also changed. Similarly, we can also write down the Fourier series in the interval 0 to 2 pi, which is given by f of x. Same Fourier series we are getting, what we have obtained for the minus pi to plus pi, where a0 is only the limit is changed. A0 is equal to 1 upon pi integration under the limit 0 to 2 pi fx dx. An is equal to 1 upon pi integration under the limit 0 to 2 pi fx cos nx dx. And bn is equal to 1 upon pi integration under the limit 0 to 2 pi fx sin nx dx. So these are some different forms of the Fourier series. In the next lecture, we discuss about some examples on Fourier series.